Hey guys, here we have a chemistry exam paper. If you want to download the paper, just check the description below the video. Boron is classified as... Okay, let's go get our periodic table. Now, boron is over here. Now, when we spoke about the periodic table in one of our lessons, we had like a line that goes like this. Okay, and what we said is that normally everything on the left is called, well, they are the metals, and then everything on the right is the non-metals. And then remember, we must also think about hydrogen. Hydrogen is on the left, but it's actually still a non-metal. But it's not as easy as that. It's not just everything on the left is metals and everything on the right is non-metals. Somewhere over here, there are some of them that are a little bit confused. They don't know if they want to be a metal or a non-metal. We call these, some people call these semi-metals, others call them metalloids. So the metalloids are actually this one, then you're going to do this one, and then you're going to do both of these, and then you're going to do both of these. Those are the typical metalloids. They are like in between metals and non-metals. They're not quite sure what they actually are. So you see there's boron, so we're going to say metalloid. Covalent bonding is now if we remember covalent bonding, so what we're going to quickly do is we're going to quickly go through the 3 types of bonding. Going to give you guys a quick little few summaries, and then we'll easily be able to answer this question. I don't only just want to answer the question, I also want to, give you the background so it all makes sense. So we get 3 types of bonding that we look at. The first one that we look at is called ionic. Then we also get covalent, and then we get metallic. So the things to remember is that ionic is when you take a metal and a non-metal. Okay. Covalent is when you take 2 non-metals, non-metal plus non-metal, and then metallic was when you just have metals, as the name suggests, metal. Okay, so I'll try to make this as quick as possible. So if we take a metal, for example, sodium, okay, Na, we can see that Na is over here. Now, if you've watched my videos before, or if you've studied this in class, we should remember that what do metals like to do? Do metals like to give electrons away, or do metals like to accept electrons? We should remember that metals like to lose electrons. Okay? They give electrons away. So that's the first thing you need to understand. The next thing you need to understand is that non-metals, let's take, so we'll use Na, and then we'll use chlorine, which is this one over here. Now, because this is a non-metal, we know that non-metals like to gain electrons. And so when you take a metal and you react it, or sorry, not react it, but when you react it to form an ionic compound, it's the perfect scenario because here you've got something that loses electrons, it loves to lose electrons, and here you've got something that loves to gain electrons. So all that happens is that the metal gives its electron away to the non-metal. So what happens is that the Na ends up becoming Na plus 1 plus 1 electron. Let me explain. Let me just actually get rid of this periodic table. So let me explain that again. The Na ends up becoming Na plus 1, and it gives 1 electron away. So remember, electrons are negative. So when Na gives that electron away, it becomes more positive. Okay? Like that. And then the Cl ends up adding that electron to itself, and it ends up becoming Cl, which is now negatively charged. We can actually just say, sometimes we don't even have to say plus 1 and minus 1. You can just do that. If it was a 2, then obviously you would need to put that. And that is exactly what happens with ionic. What then happens is that this positive thing and this negative thing, they end up attracting each other with an electrostatic force, and then they combine to become NaCl. That is how ionic bonding works. You've got a metal that gives electrons away, you've got a non-metal that gains electrons, and then those two things, the two final products, they then combine because you've got a positive and it being attracted to a negative, and then you form a strong NaCl bond. By the way, why did I only use one electron and one electron? Well, that comes down to valency, which we have spoken about. So from the periodic table, you can see how many electrons this one accepts, how many this one gives away, and that's where I was getting that. This number won't always be a 1. It depends on which atom we're using. Okay, so that is how ionic works. So covalent now is when you take a non-metal and a non-metal. So let's take the non-metal Cl once again. Now this Cl, and let's do another Cl. We can actually just do two Cls. It doesn't matter. Let's do hydrogen and let's do Cl. Now, we know now that Cl is a non-metal, H is a non-metal, hydrogen is a non-metal. So this thing needs electrons. It needs electrons, but so does this one needs electrons. So how are these two going to bond with each other? Think about that. How are they going to come together? Because in this scenario, it was very easy. One of them says, hey, buddy, I don't want my electron. Would you like it? And the other one says, yes, I would love an electron. But in this one, both of them want electrons. So how's that going to work? Well, what happens is the following. If we go draw what Cl actually looks like, we can do that by looking at the Lewis diagrams. So let's go draw the Lewis diagrams of each one. So for Cl, we know that. Now, in order to do the Lewis diagram, let me just clear this up a little bit. We need to know the valence, not the valency, just the valence electrons of that specific thing. So the way we can work out the valence is we just look at the group. So this is group 1, group 2, group 3, group 4, group 5, group 6, group 7. So hydrogen is in group 1. So if we go and draw out its Lewis diagram, we're just going to put 1. Okay. Now, if we go do it for Cl, it's in group 7. So you're going to go 1, 2, 3, 4. Remember, there's only 4 different places you're allowed to go to. Then 5, 6, 7. Let's actually do this one with a dot and this one with crosses. So this one is only missing 1. Can you see it's just missing 1 over here? Then it would be completely full because you can only have 8 going around like that. Or for at least for Cl, it follows the octet rule where it's going to have 8. Okay? So it's missing 1. And let me just show you how to explain that. If here's Cl, all of them are trying to end up going to there. So it's trying to get to group 8. So it just needs 1 more electron. So it just needs 1 more little electron over there. If we look at hydrogen, hydrogen is in this row over here. Okay, so hydrogen is also trying to get to the end. So how many jumps is it to get to the end? Well, you see it's only 1 jump. So it just needs 1 extra electron. So it needs 1 extra little electron. So what happens is that this one needs 1 electron and this one needs 1 electron. So what they decide to do is they meet up one day and they're like, hey, how you doing? Yeah, I'm good. How are you, man? Yeah, good, thanks. So, buddy, listen, I noticed that you need 1 electron and I also need 1 electron. How about we form some type of sharing relationship kind of thing here? So what happens is that this little hydrogen decides to come over here, come over here, come over here, and it arrives like that. And then what happens is that these two decide to bond into one thing, and you end up getting a molecule that looks like that. Now, all of a sudden, how many things are surrounding the Cl? 8. How many things are surrounding the hydrogen? 2. Everyone's now happy, and so what did they do? They shared electrons. Remember, these are electrons on the outside. So we're sharing electrons. So what is covalent bonding? It is the sharing of electrons. It is not the transfer. That was when we looked at ionic. That is when you transfer the electron from the metal to the non-metal. Okay? So they are sharing the electrons. I thought of a really weird story now, but let's get a little bit weird and then we'll get a little bit romantic. So let's say, for example, you've got a guy and a girl, and for some weird reason, the girl's like, I really would love a hand to hold. So the guy goes to his, his workshop, and he just cuts his hand off, and then he gives it to the girl. That would be ionic bonding. I do apologize if that's really weird. It is super weird. That would be ionic bonding. The dude literally gives his hand to the girl. But if we now want to get more romantic, if a girl walks up to a guy or they're busy chatting and she's like, I really would love a hand to hold, the guy would then just simply hold the girl's hand. So he hasn't given his hand completely away, but they're just sharing that bond by holding hands. And that's exactly what covalent bonding is. They're not giving something away, they're just sharing and forming a bond like that. Whereas if the dude literally cuts his hand off and then gives it to the girl, that's ionic, because then he's lost his hand and she's gained his hand. Does that make sense? So that's the difference between ionic and covalent. Now that's technically that question complete, but I am also going to explain metallic. If you're not interested, you can move on to the next, or you can finish this video now, or move on to the next question, whatever you need to do. But I'm going to explain metallic just for those of you that are interested. So metallic, so let's think about what we've looked at so far. We've looked at ionic, which was a metal with a non-metal. Covalent was two non-metals, and now there's metallic, which is going to be a metal and a metal. So let's say we take a metal like sodium, for example. Okay, we know that sodium is a metal, so what do metals like to do? Metals like to lose electrons. Then we take another sodium. It also likes to lose electrons. So what happens is that this Na, so they can't really give the electrons to each other, because we just said this one doesn't want electrons and this one also doesn't want electrons. So what happens is that this one over here is going to give its electron away and it's going to become positive. Who did it give its electron to? I don't know. It just threw it away. It literally just said, I'm done with this electron, and it just threw it away. And then this one does the same. It's like, well, if you're going to do it, then I'm going to do that too. So it throws its electron away. Now all of a sudden, we've got this. With metals, you can have a whole bunch of them. So we're going to have a whole bunch of Na pluses that have now developed, because you have a whole bunch of Nas that have just decided to throw their electrons away. But then what ends up happening is we end up with this beautiful structure that has a whole bunch of Nas, and all of their electrons that have been thrown away are just going to be randomly scattered around them. So there's 1, 2, 3, 4, 5, 6, 7, 8 sodium ions, or Na ions. Then there must also be 8 electrons, because each sodium gave away 1 electron. 1, 2, 3, 4, 5, 6. Okay, we still need to draw 2 more. There we go. And there we go. And this is how metallic bonding forms, because now we've got this attraction force between the negative electrons and the positive ions over here. And so what you might have seen your teacher mention is that all these electrons, they are called a sea, like an ocean, of delocal or delocalized electrons. Delocalized means it doesn't have a specific it doesn't have like a specific home. It's just floating around randomly. You cannot say that this one came from there or there. It doesn't really have a base where it came from. It's just delocalized. It's not local. It's not a local in the area. Okay, so it's delocalized. And that is how metallic bonding forms, because now you've got these negatives and these positives that are now all attracted to each other, like that. And that forms quite a strong bond, or quite a strong force. And that is how metallic bonding occurs. So it's between metals and metals. A physical change is a change in which, now before we even go look at those, let's quickly go remind ourselves the difference between a chemical and a physical change. So let's quickly just do this. So in a physical change, a nice example to use there is water. So if you have an ice block, okay, and we know that ice is made of water. So let's say in this ice block we have 20 or let's say 10 H2O molecules, because that's what water is, it's H2O. Okay, or no, let's just say there's 3 of them. So there's 3 H2O molecules. Okay, now if we start adding a little bit of heat, like maybe we go put this ice block outside in the sun, it would eventually it would start melting, and it would start turning into liquid. So we can just say liquid over here, but it's still going to be water, and there are still going to be 3 H2O molecules. It's the exact same stuff. It doesn't change into some weird like orange juice. No, it's still water. And then if you had to go and now take this and maybe pour it into your kettle, well, then you would add more energy, and you would eventually cause water vapor that you would see coming out the top of your kettle. And so now we have a situation that looks more like this, where you've got all these different little water vapor molecules, but I'm just going to draw 3 to represent that we still only have 3 molecules. Okay, so this is all a physical change. Let's just check a couple of things here. The first thing I want to talk about is that here we have 3 molecules, here we had 3 molecules, and here we have 3 molecules. So the molecules don't change. Another way is to say that they are conserved. Now, if we look at the mass, did you know that mass is always conserved, whether we are doing physical or chemical? Mass never changes. So if the mass of this ice block will actually be exactly the same as the mass of this liquid, which will be exactly the mass of this gas. So mass is always conserved, or mass doesn't change. Let's say mass doesn't change. That's easier for us to understand. And then if we look at the number of atoms, so if I look at this H2O, I know that it's actually like that. It's got 2 hydrogens and 1 oxygen. That's why we call it H2 and then O. So there are 3 atoms over there, and we have a total of 3 H2O molecules. So that means we have 9 atoms, because 3 times 3. Here we're also going to have 9 atoms, and here we also have 9 atoms. So the atoms also do not change. So the atoms do not change. Okay. The next thing I want to talk about is the amount of energy that we need to go from here to here and then to here. So if you had to go put an ice block, even if you had to go put an ice block on your kitchen counter or in your sink, would it still start turning into a liquid? Yes. We don't need to go put it, we don't need to go add, we don't need to go build a fire just to melt the ice block. So to go from here to here requires very low energy. And to go from here to a gas is, you actually don't need that much energy. Think about, I don't know if you've ever observed this, but if you've ever seen a swimming pool, did you know that many people, they put like a cover over their swimming pool? Because especially in the warmer months, the water of the swimming pool actually begins to evaporate. Now, what is that? Well, evaporation is when you are turning the liquid that was in your pool into a gas vapor or water vapor that then is able to leave the pool and turn into water vapor that then goes into the air. When that is happening, is someone holding like a fire next to the pool? No, it's literally just a little bit of energy that the sun is creating. So even to go from here to here requires very low energy. But then, Kevin, why do we have to sometimes put it in a kettle to boil the water? That is only if you want to make it happen very quickly. Then you put it in a kettle so it can happen quickly, because you don't have time to wait for like 2 days for the water to evaporate. So a kettle just makes it faster. But the idea is that it can happen with very low energy. Okay, now let's go talk about chemical change. So in a chemical change, this is where we actually create brand new substances. For example, if we are, let's say we have a fire. Now what happens is that you start off with some wood. And what would the product of this be? Have you ever seen what a fire looks like the next morning? You've got that white, gray kind of stuff. We can't really see any of it here, but you've all seen it. It's called ash. Now wood and ash, they are actually completely different things. So what we did is we took wood and then we converted it into ash. Okay, whereas here we just took water and we converted it into more water and more water. So we still had water, but here we are going from one substance to a totally different substance. So in a chemical reaction, we actually produce new substances. Another thing is that chemical reactions they need lots of energy. I mean, think about it. To convert this piece of wood into ash, you can't just go put it in the sun. You can go try. You can go put that piece of wood in the sun, and then your parents are going to be like, "Bruh, what are you doing?" And you're going to be like, "Just hold on, I'm just quickly getting ash." Your parents are going to think something's a little bit wrong. So, we need a lot of energy to be able to create new substances. So, and then there's a whole bunch more we could talk about physical and chemical, but I think we have enough information to now go and answer this question. It says that a physical change is a change in which new chemical substances are formed. That is not correct. That would be a chemical change. Mass and atoms are conserved, but the number of molecules is not. That's not true. We said that molecules don't change, so the molecules are also conserved. But here they said the number of molecules is not, so it can't be that one. Mass, number of atoms, and molecules are conserved. Hey, that looks correct. That's what we said. All three of those. So that would be correct. And then let's just see why D won't work. It says that a large amount of energy is absorbed or released. Here we said that we don't really need much energy to be able to do these things. Okay. And let me just quickly talk to you guys about this one in terms of mass, atoms, and molecules. So mass is always conserved, whether we are looking at physical or chemical. That is a universal property. Mass does not change. Atoms also do not change. That is a universal property. Atoms do not change. Okay. Now let me quickly show you what happens with molecules, because they can change in a chemical reaction. So the reaction I want to show you is, so that would be 2C4H10 plus 13 oxygen gives you 8 CO2s plus 10 H2Os. Now, this is a perfectly balanced reaction. You don't need to know how we balanced it right now. You're going to get to balancing. You'll get to that at the right time. But for now, I just want to show you something. On the left, we have 2 of this kind of molecule. Okay. You'll learn a lot more about this molecule in grade 12. So we've got 2 of those. And then we've got 13 oxygens. Okay. So how many molecules do we have on the left-hand side of the reaction? So on the left-hand side of the arrow, well, we start off with 15 molecules. We've got 2 of this one, and then we've got 13 of this one. Now on the right-hand side, we've got 8 of this one. So we've got 8, and then we've got 10 of this one. So we've got 18 molecules. So can you see the number of molecules in the beginning and at the end are not the same? The left-hand side is what you start with. That's almost like wood. And then the right-hand side is what you end with. That would be like ash. Okay? And can we see that the molecules is not the same? Whereas in a physical, it would always be the same. That is a key difference. So molecules can change. They don't have to change. Some reactions, the numbers are the same on both sides, but they can change. Okay? So this here, this one at B, this one there, sorry, that would actually be for chemical, because it says the mass and the atoms are not changed, which we said, and then the number of molecules is going to change. Well, is not going to be conserved. So it means that these molecules are going to change, and so that would actually be a chemical reaction over there. The electron configuration of a sodium ion. Okay, don't worry about the fact that it's an ion for now. Remember, an ion is something that has a positive or negative charge. Just ignore that, and let's go do the electron configuration of a normal sodium. So let's get our periodic table, And let me quickly remind you the basics of electron configuration. I love electron configuration. It is like a little puzzle that we need to solve. Let me show you how to play the electron configuration game. It's super easy. So the first thing I want you to do is just to go and highlight that one, and then all of this in this block over here. Okay, so so there we have it there. Now I want you to remember that this blue block, that all these blue blocks, they are called the S block. Okay, so all of that, we call that the S block. Now the next thing I want you to color in is all of these going down to there like that. And I want you to call that the P block. So let's call this the P block. Okay, now all that you do, guys, I love showing this. So Na is over here. So you just mark it off over there. Now what we're going to have to now do is we're going to have to start at number 1. You see how this is at number 1? And we're going to have to work our way to number 2, then to number 3, 4. Whoops, what happened there? I'll fix that now. But you're going to go 3, 4, 5, 6, 7, 8, 9, 10, and then up to 11, because that is where Na is. So we're going to have to go through 11 different things. And as we go through, we're going to start creating this kind of structure. So let's begin. So we start over here. Now, what row is this? This is going to be in row number 1. Remember, this is row 1, this is row 2, this is row 3, 4, 5, 6. You get the idea what row is, okay? So we're starting in row 1, so we put a little 1 over there. Now, what block are we going into? We're going into the S block. Now, how many blocks are we going to cross off in row 1? Well, we're going to go there and there. So we crossed off 2. Now we're going to go down to row number 2. So let's go down, let's say row 2, and we're going to enter the S block again. And we're going to cross off 1, 2. Okay, so we crossed off 2. Now we're going to stay in row number 2. So we're still in row number 2, but now we are entering the P block. And we're going to cross off 1, 2, 3, 4, 5, 6. Okay, now we're going to go down to row number 3, where we are going to enter the blue, which is the S block. And to get to where we want to go to, we only have to cross off 1 block. And so we're just going to say 3S1. Okay, but remember, that doesn't mean this is the answer. That is for a normal sodium, but they want a sodium positive. Okay, so this would be for normal sodium. Now they want it to be a sodium ion. So we need to think about what is the difference between this one and this one. Well, we should remember that because this Na is in its position number 11, it means that it's got 11 protons. And because it's a normal Na without any positives or negatives, I'm talking about normal Na, then it will also have the same amount of electrons. Okay. Now, if we look at Na+, Na+ is also going to have 11 protons. A substance can never lose or gain protons. It can only lose or gain electrons. So how many electrons do you think it has if it's positively charged? Well, it's going to have 10 electrons instead of 11. Because if it has 11 protons, which are positive, and it has 11 electrons, which are negative, then 11 positives and 11 negatives would be perfectly balanced like that. But if you have 11 positives, which are protons, because protons are positive, and 10 electrons, which are negative, then what is your overall charge going to be? What is 11 minus 10? Well, that would be a positive 1. You can think of that as a positive 1. So the point is that Na plus is going to be it will only have 10 electrons instead of 11. Now, remember that this here is called an electron configuration. Did you know that if you add up these numbers, it gives you 11? That's the way it works. So what are we going to do if we only have 10 electrons? Well, then you're going to say 2 plus 2 is 4, plus 6 is 10, and so we can stop there. We don't need this one anymore, and so the answer for Na plus would be 1s2, 2s2, 2p6, but then you would stop there because it only has 10 electrons and not 11. And so this is going to be the answer. So it's 1s2, 2s2, 2p6. It's A. If you got an answer of B, it's because you are confusing Na plus with Na. And if you got an answer of C, you are adding electrons where you are supposed to be subtracting electrons. Okay, so the answer for this one is A. This question starts by asking us to define the term compound. Okay, let's quickly go talk about compounds, molecules, atoms, so you can get a quick summary of those different things. So, if you have a single little thing, like let's say that is hydrogen, well, that is called an atom. Okay, that is an atom. And for example, if you put an H and a Cl, well, now you have 2 atoms. Okay, so and here you could have, for example, or let's say you have that, an oxygen and an oxygen, or there you have 2 atoms. So each of these little things is called an atom. Okay, now if you put 2 or more together, then we call it a molecule. That is a molecule. That is a molecule. Okay, now what is a compound? Well, a compound is like a molecule, but the atoms that you use have to be different. So for example, this one over here, this one here is also a compound because there are 2 or more and they are different. But this one over here is not a compound. Not a compound. Because there are 2 or more, there are 2 of them at least, but they're not different. They have to be different. So would this over here be a compound? Let's use oxygen and oxygen. Is that a compound? Yes, because it's 2 or more and they are different. There are at least 2 that are different. It's also going to be a molecule. So it's a molecule because a molecule just needs it to be 2 or more, but they can be the same or different. And then it's also going to be a compound. It's a molecule plus compound. Okay, so with a molecule, we can just say 2 or more atoms bonded together. But they don't have to be different. For it to be a compound, we would want it to be 2 or more different atoms bonded together. So the key difference is different. Okay, they don't have to all be different. Like here you've got an oxygen and then here you've got another oxygen, but at least you have to have 2 or more different types of atoms. Okay, so what could we put for the definition? The formal definition is that it is a pure substance consisting of 2 or more different elements. Okay, the elements are just from the periodic table. You get a hydrogen, a carbon, chlorine, neon, nitrogen, all the different elements. Okay, so for example, that is an oxygen atom, but we could also say an oxygen. It's the element of oxygen. That is a carbon atom, but it's also the element of carbon. And that is an oxygen atom, but it's also the element of oxygen. Okay, so it's a pure substance consisting of 2 or more different elements. Here we are told that the grade 10 learners mix sugar crystals with water to form a solution below. Okay, so they take water and they take sugar and they just mix that stuff together. The first question says, is the solution a heterogeneous or homogeneous? Okay, let's talk about that. So remember, when it comes to homogeneous, heterogeneous, all you need to do is the following. If we look at the salad over here, can you see different things? Well, definitely. Check here, we've got like a, what's that, a kiwi. Here we've got a strawberry. And then we've got a whole bunch of other things. We've got berries. And the point is there are different things that we can see. So that is called heterogeneous. let's look at this glass of milk. If you look at that glass of milk, it just looks like one thing. That is called homogeneous. Of course, there isn't just one thing. In milk, there's water, there's cream, there's different things. It's not just milk. It's water mixed with something else, mixed with something else. But when you look at it, it just looks like one thing. So we call that a homogeneous mixture, whereas this is called a heterogeneous. Now, if you had to imagine taking a glass of water, chucking in a bunch of salt, and then mixing it up really nicely, you wouldn't really, if you just look at it quickly, you're just going to see water or you're just going to see a solution. You're not going to see like the salt on one side and the water on one side. No, it's just going to look like one solution. And so that would be homogeneous. And the reason for that is that homogeneous things, they have uniform, that means like the same composition. It's the same everywhere, okay? Uniform composition, and all components are in the same phase. Okay. This question says, name the process that you could use to separate sugar from water. Well, what you could do is you could go put this outside in the sun, and what the sun would do is it would eventually evaporate the water. And so as it evaporates the water, what you would be left with is sugar. At the sugar would just start settling at the bottom. Okay, so you could just use evaporation. Learners were investigating the effect of temperature on ice over a period of time. The graph below was drawn from the results. Okay, so obviously I've explained this to you guys before. If you haven't watched that lesson where we talk about these temperature curves, it's very important that you watch that. I will do my best to try add a few little summaries in this one, but obviously I explain it in detail in those lessons. So what we have here in this graph, we can see that the temperature is going up. Okay, so we're starting here, and then we're ending up over here. So we can see that the temperature is increasing. So we are going to be taking a block of ice, and we are going to be turning it into liquid, and then turning it into water vapor. And this graph helps us to understand the process and all the different things that are going to take place from the block of ice all the way to the vapor or the gas. Okay, so it says for the first question, define the term molting. Well, we know that molting is when you go from a solid to a liquid. So we can say that it's the temperature, because they said the molting point. It's the temperature at which a solid becomes a liquid. This one, in which phase is the substance at, in which phase is the substance at in point 1? So point 1 is over here. So is it in the solid, liquid, or gas? Well, if you've watched the videos where I explain these curves, you would understand that right here at this very low temperature, at this phase over here, we are in the solid. Okay. Then this phase over here, we are in the liquid. And then in this phase over here, we are in the gas. This area over here is where we are going from solid to liquid. So that is where we are busy switching over. And then this area over here is where we are going from liquid to gas. So in which phase are we on in point 1? We are in the solid phase. Okay. Now it says name the process at point 4. So at point 4, we are going from a liquid to a gas. Think about if you put water in your kettle at home and you turn it into, you start boiling it, it turns into a gas. That's why you see the steam coming out the top of the kettle. That is called boiling. Okay, now obviously I could go into way more detail, but I've made a full-on video about this already. So you just go find that and then this will make sense, okay? Now this question says, on point 2 on the graph, so point 2 is this one over here, where we are busy switching from a solid to a liquid. There is no change in temperature. Explain this observation. So this is the really interesting stuff in that this area here, we can notice that the temperature is not changing. Can you see that? When you are changing from solid to liquid, temperature doesn't change. And also when you go from liquid to gas, temperature doesn't change. And that's what we're going to go talk about now. So let's quickly talk about this little area over here. This little portion here from A to B. So from A to B, we are in the solid phase. And so that would be like a block of ice. Okay? And what we must understand is that that block of ice has a whole bunch of water molecules. So let's just draw them like this. Okay, a whole bunch of water molecules. And those water molecules, or what's going to happen is that as you start adding in heat, so let's draw like a fire. Okay, there's a fire. That's going to start adding heat into that ice block. The ice block, well, what happens is that the individual molecules, as you start adding in heat energy, they're going to start vibrating a little bit faster. Because they're in the solid phase, they're not moving around. They're not moving like from here to here. But what they are going to start doing is they're going to start vibrating. And they're going to vibrate faster and faster and faster. And the temperature is going to begin to rise. Okay? Now, as you get to point B, where we've reached for water, which is at 0 degrees Celsius, what's going to start happening now is the intermolecular forces, which are the forces that are in between the molecules. They are the forces that are holding the molecules together. They are called intermolecular. Okay? What starts to happen now when we get to 0 degrees is the energy is going to start, you can think of it as almost like breaking those, and it's going to start pulling these molecules further away from each other. Okay? In the part from A to B, that wasn't really happening. That wasn't happening. So all that was happening was the energy from the fire was just causing the molecules to vibrate faster and faster and faster. So because they were going faster and faster and faster, the temperature was increasing, because that is what temperature is. Temperature is a measure of the kinetic energy of the molecules. So they were just going faster and faster. But now when we get to this area over here, what now happens is that this energy that is now coming in is no longer going to be used to make the molecules go faster. What that energy is now going to be used for is to start overcoming these forces of attraction between the molecules. And it's going to start pulling the molecules apart. So even though more energy is coming in from the external, we're adding in more energy, the molecules are not going to be moving faster and faster and faster in this process over here. The energy that is coming in from the outside is used to now move the molecules away from each other and start turning them into a liquid. So we are going to notice on the graph that the temperature of the molecules is not going to go up, because they're not going to start moving faster and faster and faster. So we're not going to see it increasing like we do over here and over here. Instead, that energy that is coming in from the outside is going to be used to overcome these forces. And so the temperature remains constant while we are converting from a solid to a liquid. So what we can say, because remember guys, this temperature is not the temperature of the fire or the external heat. This temperature is a measure of the kinetic energy of the molecules. Remember, that is what temperature actually is. It's a measure of kinetic energy. So in this period over here, from here to here, the molecules are not going to begin to move faster and faster. They're going to stay at the same kinetic energy that they were at, but they're gonna now start moving away from each other. And so this energy is now being used to separate them. But that energy is not now making them move faster and faster and faster, like we saw in the earlier part over there. Okay, so the temperature remains constant. So why is this happening? We can say that the substance is changing from a solid to a liquid. We can say kinetic energy, which is the kinetic energy of the molecules, remains constant, And there we go. That's all we have to say. So because the kinetic energy is constant, the temperature remains constant. So let's just say, therefore, temperature remains constant. If this one was worth more than 2 marks and was like a 5-mark question, well then obviously you would have to go into more detail, okay? But I have explained this in one of my previous lessons, but I have also explained it here exactly what's happening, and that this energy is being used to overcome those forces of attraction. This one says write down the molecular formula of ice. Well, ice is just water, so you're just going to say H2O. 2 isotopes of carbon are represented below. First question says define the term isotope. So let's quickly talk about isotopes. So if I, for example, show you, so let's say, for example, I show you fluorine, okay? Now fluorine is over here. Now if I show you using the, there's that notation where we can show the mass and the proton number, where we use that like AZ notation, AZ, where this top one is the mass number, and then this bottom one is the atomic number. And so, for example, if we look at fluorine, now what's weird is that you have to actually switch these numbers around. Remember, if you look at fluorine, that is the atomic number, that is the mass. So we would put so fluorine would be 19 and then 9 over there. So the bigger number is always the mass number, and the bottom number is always the atomic number. So remember, what gives an atom mass? We know that an atom consists of protons, neutrons, and electrons. Can you remember which of those have no mass? Well done if you said electrons. Electrons have no mass. So the only thing that is giving something mass would be protons plus neutrons. So that means that gives you 19. And then this over here is your, this is also called your mass number. This one here is called your atomic number, but it's also the number of protons. Okay, it's also going to be your protons. So if we look at this now, we know that it's got 9 protons and it's got a total mass of 19. So it's already got 9 protons. So how many neutrons does it have? Well, it would have to then have 9 protons, like we said, and 10 neutrons, so that the total mass is 19. Okay? So what would this then be if I gave you 20 F9? So now what happens now is that it's still going to be fluorine. It's still got 9 protons, but now we can see this number has gone to 20. So that means we've got 9 protons, but that means we now have 11 neutrons, so that the total mass is 20. And these are going to be called isotopes. Isotopes are the same element, so it's fluorine and fluorine, same proton number. We never ever change the proton number. Please listen to me. We never change the proton number, but we can change the neutron. We can change the neutron number, and when we do that, these things are called isotopes. So isotopes are the same element, but with different amount of neutrons. So now we can begin. So what are isotopes? Isotopes are atoms of the same element, like I showed you fluorine and fluorine, with same number of protons, but different neutron number. Okay, this one. How many neutrons are there in a carbon-14? So here's a carbon-14. Now remember, this is your protons. Technically it's your atomic number, but it's also going to be the same as protons. And then this is your mass number, which is your protons plus neutrons. Okay, that's what we spoke about now. So if it has 6 protons and its overall mass is 14, well then it has to have 8 neutrons. So we can just say here 8. Now this one says draw the Aufbau diagram. What is an Aufbau diagram? The Aufbau diagram is that one that has the blocks like this with the arrows, Some of the arrows are going up, some of them are going down. That is the Aufbau diagram, okay? To be able to draw an Aufbau diagram, you also need to be very good with electron configurations. You know, the thing that goes like 1s2, 2s2. So we need to go talk a little bit about that, and then I'll also quickly talk about Aufbau, and then we'll complete this question. Oh, here they're also asking us in 4.4, write down the SP notation. That is the electron configuration. So we're sort of going to tackle both of these at the same time. So let me quickly give you a quick reminder of how electron configuration works. So let's say, for example, we are going to look at AL. Okay, so that's the goal of where we're going to get to. Now, remember we said that this one, and all of this, we said that that is all called your S block. Okay, and then all of this inside here, that is, all of those are going to be your P block. So obviously I've made videos on this already, so you can watch those, but this is just a quick explanation, a reminder. So the way it works is, if we're looking for aluminium, which is over here, we can see that, well, yeah, that's where it is there. So we always have to start up here at the top left. So we always start here in row number 1, and we start in the S block. And in row number 1, we're going to go 1, 2. So that was 2 things that we crossed off. Now we go down to the second row where we go to position 3. You see how we started at position 1, then position 2. Now we're going to go to position 3, 4, 5, 6, all the way until we get to 13. Okay, so now we are in row 2, and we are entering the S block over here. Now in the S block, we're going to cross off 1, 2. Whoops. Now we're still going to be in the row 2, but now we're entering the P block, and we're going to cross off 1, 2, 3, 4, 5, 6 things. So we're going to do that. Now we're going into row number 3, where we're going to enter the S block, and we're going to cross off 1 and 2. And now we're still in row number 3, but we're going to enter now the P block, where we're going to cross off 1 thing, and then we are at aluminium. So that is the electron configuration of aluminium, for example. Now to do the Aufbau diagram, you're going to go put each of these things. So we're going to start with the S, 1s, then we're going to have 2s, then we're going to have P. Now whenever there's P, you're going to put 3 of them. Then there's 3s, and then there's 3p again, so you're going to put 3 of them. So the p's always have 3, okay? And then your teacher might want you to write energy over here. Some teachers do, some teachers don't. And then you draw an arrow going up. Okay, so we know that we are going to go, the S2 is gonna have 2 electrons like that. This one is gonna have 2 electrons. In the P, there's a total of 6, so 2 each. In the S, there's gonna be 2. And then in P, there's just gonna be 1. And so that is how we go from a electron configuration to a Aufbau diagram. Okay, that's the summary I wanted to give you. Now we can go do the questions from this paper, or from this question. Okay, so this question says, draw the Aufbau diagram for the normal carbon 12. So that's just the normal carbon 12, which we have over here. And so once again, if you remember how I did it now, so we're going to enter at row number 1. So this is the electron configuration. So this will actually be the answer for this one. So you're going to enter at row number 1, and you're going to cross off 2 of the things from the S block. Then you're going to enter into row number 2, where you're going to enter 2 things on the S block. And then you're going to enter still into row 2, but now you're entering the P block, which is this part. And we're going to go 1, 2 things over there. So that over there is the electron configuration. Now we can go do the Aufbau diagram. So you see we have a 1s block, then we have a 2s block, and then we have a 2p block. Boom, boom, boom. So with P, you always put 3. So that's your 1s, 2s, 2p, and then going up is energy. Okay, so in the 1s block, there's 2 electrons. There's something very interesting coming up now. Over here, there's 2. Now, here we only have 2 electrons. So what are we going to do? Well, the wrong way would be to just put them both over there. There is something called the Hund's rule, which pretty much says that we should do the following. Always full 1 electron per orbital at a time. Each of these blocks are orbitals, so you only put one at a time. So in the p block, we put 1. Then you go to the next one, 2, and there we're done. We've got 2. If there was a 4 over here, then you would go 3, and then you would go put a 4th one in there. Okay, so you first put them individually, and then once you fold up, then you go and join them up. Then you go add a second one per orbital. Okay. The following diagram shows the synthesis reaction that occurs when hydrogen burns an oxygen to form water, and it also releases heat and sound. The unbalanced equation is given below. Balance the equation. Okay, so remember, I've got steps that I've given you guys for how to balance equations. So if you've watched my video on balancing, well, these are the steps that I like to use to balance an equation. So step 1, we balance all the metals. Now let's get our periodic table. What we should identify is that there are no metals over here, so that's done. Then it says balance all the non-metals except for hydrogen and oxygen, but we only have hydrogen and oxygen, so that step's done. Step 3, balance hydrogen. Okay, so we're going to balance hydrogen first. So on the left hand side I can see there are 2, and on the right I can see there are also 2, so those are balanced. And then now we're going to balance oxygen. So on this side I can see that there are 2 oxygens, but on this side I can see there's only 1. So the way that I fix that is I can't put a 2 here. No, I'm only allowed to put numbers in the front. Okay, so what I'll do is I'll put a 2 over there, because now we've got 2 oxygens, but now all of a sudden the hydrogens are not going to be balanced, because now we've got 2 over here, but over here we have 4. So to fix that, I put a 2 in the front. Now we have 4 hydrogens on the left, 4 hydrogens on the right. We've got 2 oxygens on the left and 2 oxygens on the right. And so that is now balanced. Okay, so we've done this one. Now name the phase of the water. So water could be solid, liquid, or water vapor. But if you look here, they said water vapor. So you can just say gas. Draw the Lewis dot diagram of oxygen. All right. To do a Lewis diagram, so for example, we're doing it of oxygen, you're just going to put the symbol, so oxygen, and it's over here. Now you just need to go look at its valence electrons. So that you just do like this. Hydrogen has 1, or sorry, all of these have 1. All of these have 2 valence electrons. All of these have 3. All of these have 4. You get the idea. 5, 6, 7, and 8. So I mean the entire group when I say that. So oxygen, you can see, has 6. So how do we do this? Well, you're going to start by plotting 1, 2, 3, 4. You're only going to go to those 4 places. Now that those 4 places are complete, now you start going around the outside. So 5, 6. So that is what the Lewis diagram of oxygen will look like. Now they want us to do it with water. Now we know that water is H2O. So let's go do a hydrogen like that. And then, for example, a hydrogen over there. Now let's do it with a different, let's do X's for these ones. Now when you put H2O together, there's 2 hydrogens and 1 oxygen. So you'd have to put all of that together. Let's just quickly first go write out the answer for this one. Boom, 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 boom. Now, how are we going to put all of these together? Well, all that would happen is that these 2 over here are going to form a bond, and these 2 over here are going to form a bond. And so you're going to end up with a structure that looks like this. And there we go. That is the Lewis diagram of water. So we can just fill that in. Boom, 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 boom. Boom, boom, boom. There we go. This question says, is this reaction endothermic or exothermic? Okay, so endothermic, these reactions absorb energy. Exothermic, release energy. Now they said that this reaction releases heat. That is a type of energy. So because it releases and not absorbs, we say that this is a exothermic. 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 Calculate the molar mass of water. So to find the molar mass of water, we know that water is H2O. So we're going to go get hydrogen, which is over here. And we're going to get its mass, which is this one here. And there's two of them. So we're going to say 1 plus 1, because there's two of them. And then we're going to do oxygen, which is over here, which has a mass of 16. And that's going to give us 18. Now the units for molar mass is grams per mole. When a lead nitrate, so lead nitrate, lead is Pb, nitrate is NO3, and potassium, which is K, and iodide, which is I, when they react, a yellow lead iodide, so that's going to be this one over here, and precipitate forms as one of the products. They called it a precipitate because it's a solid. Precipitates are solid. So just once again, lead nitrate is this one. Potassium iodide is that one. And then lead iodide is one of the solutions, which is that one. Okay, and that one they said is a precipitate because it's got a solid, as we can see. The first question says, what does AQ represent? Well, AQ represents aqueous. I always struggle with the spelling of that. It's something like that. Define the term mole. Okay, I personally don't like the definition of mole because it's really weird to understand. So I'm not even going to go into the details of it, but this is the definition. Your teacher might use something slightly different. 1 mole is the amount of substance having the same number of particles as there are atoms. Yeah, so that's quite a complex one, but I would just say you should just like memorize it. Of course, we could go into the details, but even if I go into the details, it still is a very weird definition. It's not that popular as a definition, so I'm not going to go too far into that one. Okay, let's move on. So this question says, if 30 grams of lead iodide, so lead iodide is this one, so we've got 30 grams, is formed, calculate the number of ions, iodide ions, present in that precipitate. Okay, so if we look at PbI2, if we just have a look at a close look at it, it looks like this, PbI2. So what I want you to realize is that it's got 1 Pb, which is here, and then it's got 2 iodines. Okay, so there are 2 iodines. So for every one of these, it's got 2 iodines. So let's go look at now, they've given us 30 grams, and they're also talking about the number. So we're definitely going to have to do stuff with moles. So we've got this formula here, which helps us with moles and number. And then we've got this one that also uses mass, because they've given us mass. So let's quickly go circle everything we have. We have this, that is just Avogadro's number. It's a number that is on your formula sheet. We can easily get that. That is just from the periodic table. And they've given us this. And what we're trying to find is the number. So we're trying to find this. So can you sort of think about how we're going to combine these two equations? Well, can you realize we could use this formula to calculate this, and then we could put that over here, and then we could find this. So step 1 is we're going to use this formula here. So we're just going to say N equals to M over capital M. Now, they gave us the mass as 30. Now, this mass is on the periodic table. It's the molar mass. So let's get our periodic table. And we want to find the mass of Pb and I2. So Pb is lead. Where are you now? Oh, here's lead over here. Okay, so it has a mass of 207. And then we've got iodine, which is over here. But we've got 2 of them. So we're going to say 127 times 2. Okay, and if we had to work this all out, we should end up with, now we don't want to round off just yet, so let's just say 0,065 0759. Okay, that is the moles of PbI2. So now that is we now have the N of PbI2. Okay, so now we can go fill that in this formula. And remember, I've taught you this before. That formula comes from this triangle. So if we have this and we have this, how do we get this by itself? Well, you have to multiply these two. So we're going to end up with a formula that says that. Okay? And so that's going to give us the number of moles, which is 0.0650759, multiplied by Avogadro's number, which is 6.02 times 10 to the 23. Remember, it is given to you on the formula sheet. 6 times 02 times 10 to the 23. Sorry, guys. Let me write that a bit better. 6.02 times 10 to the... Take 3. 6.02 times 10 to the 23. So you're going to multiply those two numbers together, and we should end up with the number of particles as... Okay, we can round this to 3.92 times 10 to the 22. So that is not the answer. That is the number of these ones. But we said for every one of those, there's 2 of those. So we're just going to multiply this answer now by 2. So the number of iodides is going to be equal to that number multiplied by 2, which would then end up giving us 7.84 times 10 to 22. And now this last question says, what is the mass of potassium iodide that would be used to prepare the potassium iodide solution? Okay, so they said that we have 30 grams of lead iodide, which is this one. Now remember, I've taught you this before. Once you can calculate the moles of any one of these, then you can use the mole ratios to get the mass or whatever you need for any of the other ones. So we know this information over here. So from that, we can work out the moles of that. But we already did that over here. So we have the moles of potassium iodide. So if we look at the ratio of Ki to potassium iodide, let's just quickly go write this down. We have 0.0650759, and then the moles of this one we don't know. And we can see from the balanced equation that the ratio is 2 of these for every one of these. So that means that for every one of this one, there's 2 of this one. So we're going to take this number and we're going to multiply it by 2. So we're going to say the moles of potassium iodide is going to be 0.0650759 multiplied by 2. And that's going to give us, you can just round that to 0.13 moles. So now we have the moles of this, and now we just need its mass. So we've got this formula. Now that formula comes from this triangle, where this is mass, this is molar mass on the periodic table, and this is moles. So if you want to get this one by itself, you have to then end up multiplying. So we need to go and get the molar mass of potassium iodide on the periodic table. Okay, so if we're looking for potassium iodide, potassium is this one here, and then iodide is over here. So the mass is going to be 39 plus 127. So we could say that the mass is going to be equal to the moles, which is 0.13, multiplied by the molar mass, which is going to be 39 plus 127, and that will end up giving us 21.58 grams. And so there we have it. We've calculated the mass of potassium iodide.